Okay, starting the recording here. Okay, so let's share the presentation here. Um, we are going to look at the reinforcement learning introductory class. As last time, we seem to have some problem during the presentation, technical problem. So uh, no problem if we go over some of the concepts one more time. Reinforcement learning, this is an introductory class. Uh, um, so what is reinforcement learning? The definition, application. What is reinforcement learning system? And we'll talk about the agent and the agent component. Okay, so if I may use a pen here. Okay, so these are basically my references. Okay, all right. So there are along the textbook. I probably should add the textbook that I used in this lecture. Okay, the best and optimum solution. So here is an introductory puzzle. What is the best possible solution to this puzzle? Or the best path to solve it? And obviously, you can always for us this is very simple. You can go, okay, so well, this is the path. That's easy. But this conceptualize a class of problems where we needed to do a sequential stepping to find the optimum path for this sequential steppings. Okay, so the optimum way from start to goal, that's sequential steps, and the solution is offered by reinforcement learning. A lot of times students bring up issues like what is the difference between the reinforcement learning and let's say, for example, routing algorithms, because we do have routing algorithms. And the answer is the reinforcement learning is supposed to give you a intelligence to interact with many parameters, and based on the learning that you have put into this machine, it will choose the best path. Routing algorithms, they are the intelligence is handcrafted. We put the intelligence in them, but in these systems, what you do, they learn and they take the decisions on by themselves when they are deployed on the field. Okay, so and it will be apparent in the next example. So in this best optimum solution, so this puzzle, okay, what are the possible solutions? So here is an example that we use. Probably I should choose a different color if I can. Let's say if I can. This is an example that we'll choose. You have a class where you have to take three classes, class one and class two and class two and class three. Then you have to pass an exam and then you go on sleep. There are distractions in this process, okay? And this distraction is the phone is one of them, and probably the cafeteria is one of them. Okay, so based on these distractions, okay, I built this process where I describe states, right, and probabilities, the one in the black, and rewards, the one in red. Okay, and we want to find out the solution that we can be rewarded the most. This is what reinforcement learning methods. It provides me with the solution that rewards me the most. Okay, and this hopefully the optimum solution. So reinforcement learning is a machine learning training method based on rewards. Okay, you have to tell me if I take a step front or to the right or to the left or back, which of these steps as I stand in my position and my state, and I want to transition to another position, to another state, which of those steps I will be rewarded the most. Okay, so we will use rewards, okay, to train the algorithm. So there are similarities between reinforcement learning and supervised and unsupervised methods. So in terms of unsupervised methods, they we use these rewards. We direct the unsupervised machine through the rewards, right? We don't have a ready-made classification for the right answer. It's not so that's in that case we don't have labeled data set for the system to learn. On what we have is rewards. And it is similar to the supervised learning from the sense that you have to give goals and rewards. You have to provide those, much like we provide labeled data sets. So we have to do something. It's not like you deploy this in the field لحالها without any work. So you have to provide the upfront work of determining what are the goals of this game, the goals of this setup, and provide rewards so that the system, when it get trained, it will learn the optimum path, the optimum solution. Also, for example, in a chess game, the goal is to beat you. That's the chess game. Okay, the goal is to beat my opponent in the chess game. So we have to set up these goals and rewards. Okay. But once it learned those on its it learned the game through the goals and the rewards, it's supposed to work on its own. Okay, so that's basically the promise. Okay, we have many applications for reinforcement learning, gaming, robotics. We have reinforcement learning have been tried recently in solutions for pharmaceutical companies and medical applications to study proteins and all that stuff. Very complex medical problems, in fact. Okay, so what's a reinforcement learning system? What are the components? Well, to start, you must have the environment, okay? And second, you must have the agent. And the agent is what we are trying to train. And the environment is everybody else. So what I am trying to train is my agent, is where I want to put the intelligence, where I want to put the training into. Okay, the environment is what it interacts with this agent. Let's say, for example, I want to have a robot system which can move around this class, and maybe this robot system is supposed to monitor or proctor an exam. Okay, so it has to go through the lines and grids, right? So it has to know where the obstacles are. Okay, so in this system, uh, the robot is my agent. The robot is my agent, and everybody else, which is the class in this case, is the environment. Okay, so typically the environment provides to the agent the observation. Okay, so the observation is basically it tells the environment, tells the robotic system what it is. So in this case, you can stick a camera on the robot system, and it will know what it is. Or for instance, you provide coordinates to the robot system what it is inside the room. There are many ways to do it. Okay, so anyway, the environment through sensory equipment, it knows where it's positioned. All right, then it will take an action. All right, an action meaning it will step to the front, go to the back, take right, take left action. Okay, so that is the action that this robot is taking. And then once the robot takes the action, the environment gives it to reward. Yep, this is correct. Or I'm going to give you a reward of 1, or 0. I'm not happy with that move. So along the way, the system learns that what are the best moves and what are the bad moves. It's exactly like how a child learns behaviors through talking to others, through talking to parents. And when the child, for instance, in a healthy environment, when the child, for example, yells and shouts, then everybody becomes unhappy. So the environment gives bad or negative rewards. So that child knows that raising the voice is not appropriate. Okay, so so next time it will not raise the voice for when it's talk. So this is basically the principle that we are talking about here. Okay, so so the RL system consists of an agent, which its purpose to maximize future rewards. That's basically our goal. And the environment, everybody else. So you can say the environment is the world minus the agent. That's basically the definition of the environment. Everybody else, okay, or everything else. And now events move from step one. So in these typical systems, we kind of, I hate to use the word discrete, but this what we do, we discretize the time. We assume that we are in step one, then step two, and then step three. Okay, all right, time-wise. So we refer this to this T, right, as the time step. So when we talk about T plus one, that means the next time step that comes after T. Okay, so that's basically what we mean by that. Okay, so events in each steps are ordered. Okay, all right, and the order of the events are as follows. The environment, as I said, environment provides the observation. Okay, so and the rewards from the previous step. Okay, so these are the kind of things that the environment provides, and then the agent takes an action. Okay, okay, and then we move to the next step. So the environment provides what? The state, the observation, and the reward for the previous action. And then the agent digests this and take the next action, which is here. So notice these arcs: observation or states, rewards, right? And then action. Notice the action goes to the environment, and that makes sense because when the child talk or screams, that child screams at the environment. Okay. All right. So if I'm training the child, the environment becomes the world minus the child. Okay. All right. So this is basically the reinforcement system. And inside this agent, we're going to talk about something referred to as the state. So the state of the agent and the agent state, sorry, and the environment state. We will talk about policy, value function, and model. And all of these are different methods of implementing the intelligence. You can use one of them, all of them. Okay. All right. And so the history of sequence in this environment goes, environment provide observation. Let me choose, if I can choose a different color here. Oops. So the environment provides the observation and the reward, and then the agent takes an action. Then the environment provides observation, rewards, the agent takes an action, and etc., etc. So this is the way as we explained in the previous slide. The state is a function of a history, so it determines what is the next step. So I have to, the state really is the function of the history, and we give this because this is a Markov machine. We'll implement it with a Markov machine, and we will get into the definition one more time into Markov state machine. We say that the Markov property is that the state has all the history of the previous states, and we give a good example for that, although it's not very accurate example, is the counter. And we say if we have if our counter has the value of 5, that 5 means that we have already counted from 0 to 1, 1 to 2, 2 to 3, 3, 4, and 4 to 5. So that is inherited in that state. I don't have to tell you when you look at and see that the counter value is 5. All these steps have been taken and it is inherent in this state. So that counter has a Markov property. Okay, and so we'll see that in the follow-on lecture. Now, one thing here is that the environment state is the environment internal representation. It represents and produce. So the environment state here, let's say to simplify it, let's say, for example, I am implementing a system to play a chess game. So for me now, this is the opponent in the chess game. And this is the system that I'm building to beat this world champion. So that world champion has a state in his or her mind. Okay, so this is the environment state, okay, where the thinking process happens, right? And I have my agent state, which is the state that is inside my this object that I'm trying to make it intelligent, that I'm trying to make it smart. So this is that state. So the environment state is the environment internal representation. Okay, so that's key here. But the agent state is the agent internal representation. And you would hope that you can capture as much of the environment internal representation as you can. Sometimes you cannot. Okay, and so very shortly we'll talk about a model-based or model-free. Okay. I'll talk about these examples. For instance, you can think of if we have a robot that can be deployed in any location, right? And I can give the map of that location to the robot. So I'm giving this model representation of the environment to the agent, or in model free solutions or agents, I can deploy the robot and say, learn the environment. You have to discover this class. And you can see this in some of these devices that they sell for houses, for cleaning the carpet or what have you. They deploy this product, and then it spends 2 to 3 days learning your house, learning your apartment. And then once it learns the model, right? Okay, so obviously we didn't give it to the model, right? Because when they manufactured this product, they didn't know all the houses in the world. Okay, so this product, when it's deployed, it doesn't have the model. It learns the model. It learns the house, the topology. This is a place where I clean. There's an obstacle here. This could be a sofa or a bed, so it stays away from it, etc., etc. Okay. Markov state and Markov decision process. Now, Markov decision process are these are the constructs that we will use to build our agents. Okay, and obviously the information state, which is what we would refer to as Markov state, is the state which contains all the information from history, as I have given the example of the counter. So the information state, or the Markov state, is a state which contains all the information from history. We gave the example of the counter. For example, another Markov state is we can use it, is when I say that this student is a graduate student. That implies they finished classes for first year, second year, third year, and almost fourth year classes. I did not need to tell that. So that state of your academic state is a Markov state because it implies the history behind it. It implied you have finished high school, right? It did. It does. Right. So the Markov state, and the beauty about these Markov states is that you don't have to tell the history. Because if I have to tell the history, it means I need, if I want to represent this machine, I need memory. And keeping track of the memory for all the moves that you take is very expensive. And that's why we love those Markov state, because you don't need the history. Only what you need is the current state. I don't need to tell you the history of this student. All what you need to know is has completed all the coursework for a bachelor degree. Done. Okay, Markov state. Okay, so that's the beauty about Markov state. So the future is independent from the past, giving the present. So for example, when I say somebody graduated from our program, okay, the future of this person dependent on he got this degree. right? Doesn't depend where you were born, what year you were born, and what year you finished your high school. Now you have this state that we will build future predictions or future action based on this current state. Okay, so formally we say that if we are in state ST, right, that our current state depends on, okay, so the probability of going to, so let's say this is ST, all right, and we are, what is the probability we will go to this, let's say ST plus 1, or let's say, for example, T plus 1 prime here. So the probability of going to from ST to ST plus 1, meaning from current state to futuristic to future state, is only dependent on the current state. Only dependent. It doesn't depend on history. Can you be employed? Well, it depends on my current state. I finished my bachelor degree or I did not finish my bachelor degree. It doesn't depend on the history. So the probability of going from state ST to ST plus 1, that's what the notation means. It is equal to the probability if I give you all the history, right? Okay, given all the history, I'm going to transition to state ST1. So meaning this history really is redundant. Just give me the present state. Okay, so that's what it means. So Markov decision process is when agent state equal to the agent environment equal to information state. We aim to having the state that is inside the environment to be part of the agent environment. And that's a tough challenge. Okay, that is a tough challenge. Okay, now, so our goal here is that we want to build Markov decision process, because this is how we will build agent for reinforcement learning. However, let's see where that Markov decision process came. So initially, we start with all these stochastic or random processes. When you design reinforcement learning, you assume that the environment is not predictable. Well, for instance, when I deploy this cleaning machine, and this cleaning machine doesn't know the house, it's random. Even when it learned the topology of the house, we can change the place of the sofa. The sofa could be here. We can change it to different place. So it has to learn, even after it has learned the topology of our house. So it's a random process. When I deploy a robot that goes from here all the way to the deanship, right? There can be crowd outside, or it could be empty hall, even if it knows the topology of the building. So even if it knows, I'm not sure if you have seen, but some of those robots that they show in the convention centers or for conferences, it zigzags between people. There are people talking, then it goes around them. It doesn't, it doesn't hit them and go through them. So all of this, the environment is random. So we start with the stochastic process, and then we assume that we have Markov property, which means the position, the state that I am in, implies that it is enough information for me to know the present state, and I do not need the past. This is very beautiful for me as far as computer science and engineering is concerned. Reason, I don't have to have all these moves, right? And that if I have to, it means I need a large memory, a very large memory. So suppose, for example, I am running this robot for 10 years, then it means I have to remember all the steps that this robot has made in the last 10 years. If it had not been a Markov process, but a Markov process, don't worry about it. It's enough to have the present state, okay, to make your next state. So that's the beauty. So once, if I have Markov property, then I'm going to call myself a Markov process instead of stochastic or random process, because Markov process is a random process which has the process of Markov property, which means the states in this system You don't need to remember the history. Only what you need is the present state. Now, if you add rewards, we'll say that your Markov process becomes Markov reward process. If you add rewards, meaning if you take this direction, I'm going to give you this reward. So I'm a robot here, and I want to take a step forward. You tell me you have a 1 point reward. But how about if I take right, you have 2 points reward. If I take left, 0 reward. If I go back, you have -1 rewards and -1 for punishment. Yani this is how mathematically we so now if I add rewards to the states, it becomes Markov reward process. Now let's add to Markov reward process actions. If I have states and I have rewards and I have actions, then in this case, Markov decision process is what I have, right? It is, so Markov decision process is what? It is a Markov action plus Markov property, and Markov property is what? It is a Markov process plus rewards, and Markov process is a random. So basically, Markov decision process is what? It is a stochastic process with Markov property, with rewards, and with actions. And this is what I want. Why this is what I want? Because this is when you tell me if I take an action of moving forward, what's the reward? Okay. Not only I'm moving into a next state, I'm taking action. Okay. So these actions become, in the case of the chess game, I'm taking an action of moving one piece of the game from one position to another position. That's an action. Okay. All right. We'll see. We'll see how. We'll see how do we program their words. A good question. We'll see how. We're getting a little bit ahead of ourselves, but we'll see how we'll program those. Okay, so an agent component. Let's now focus on the agent. How do we implement the agent? The agent it includes the agent state. Okay, and it can include a policy, and we will see how that implemented, or a value function, or a model. Okay, all right. So um, it can include one or two of those two, but you have to at least to have one, and we'll see how that works. Now we in our discussions in the next lectures, we're going to talk about policy, okay, and we will represent this as a pi. So pi and an S in between, that is a policy. So what is a policy? Let's say, for example, when I let's see if I have an example here. No, okay. Okay, so here we have a policy says, for example, that in my position right now, where I stand, I can take either front step or right step. Okay, in this position, like in the next position, let's say I took one step to the front here, and what's the policy here? You can go right or left. That is a policy. Okay, this is what policy. It gives you what you are allowed to do in a state, and it will be very clear with the futuristic examples that will take them. So the policy can be deterministic or stochastic. Okay, can be deterministic or stochastic. So for example, I can tell you you can take a step front or right, equal chances, or you can take a step forward but with this probability, and take a step right with this probability. It can be stochastic. Okay, so this is a we call it agent policy. We have the value function. Okay, so the value function is the prediction of the future rewards. Okay, so the value function of a state. All right, so every state, you will see the value function coming in two places: a value of the state and a value of the action. Both of them وجهين لعملة واحدة. The value of the state or the value of the action. And why we need to know both? Because we will see that algorithms are geared towards computing either the value of the state, and some algorithms are geared towards computing the value of action. For example, one of the algorithms that we will learn in this course is Q-learning. Q-learning is very powerful algorithm for reinforcement learning. It is based on the value of the actions, which it inherently has the value of the state. Okay, so that's why I say, if I give you the value of the states, you should be able to compute the value of actions, as we will see. If I give you the value of the actions, you should be able to compute the value of the states. So what does it mean when I say the value function of the state, which is VS? It is the prediction of the future rewards. Okay, so if I am in this state here, what is the total rewards for me that I can collect if I reach my goal? Which means, let's say, for example, if I take one step, two step, three step, every step I take one reward, two rewards, three rewards, three rewards, until I get my goal. So I'll say, oh, if I start from here and I get to the door or to my goal, I'm gonna collect 10 rewards. What about if I take other roads? I'm gonna collect 9 rewards. So how do I compute then the value of the state? I will run 100 random trials, and then I say the average of those طلع معي 7. That's the value of the state, which means as I start from here till my goal, what is the value of my reward? طبعا you can see that هنحكي عن rewards. Oh yeah, because our algorithms, we are trying to maximize the rewards. Exactly like the child لما يصيح ويطلع صوته, you kind of تعطي الوجه العابس negative reward. لكن لما الطفل مثلا يحكي give a nice words or a thank you, تعطيه الابتسامة. This is the positive rewards. So then now the child knows that the state of talking nicely is a good state, has high rewards, and the state of shouting is not a good state. It has a negative rewards, because internally the child summed the rewards, right, for yelling, and it ended up being negative rewards. And internally in the mind of the child, sum the rewards, right, of saying thank you for any person or good morning, and that ended up being a positive rewards. And this is how ولذلك بيسموه reinforcement learning المعزز, right? Reinforcement learning. It depends on the rewards that the child. ولذلك if you see somebody who yells all the time, you have to be positive. And this person came from an environment where everybody yells at everybody. And it is good to yell. Otherwise, that person wouldn't be doing the yelling, right? Okay, so the environment that person came from, yelling was a positive reward, and that's why it became part of the communication process. Now, so the state mathematically هلا, the value of the state, we sum all the rewards starting from the state. Now لاحظ here what we do, the expected, which means I run too many values and I take the average. So this E here, it means averaging of all the patterns or all the scenarios, a better word, which started from this state until my end goal. Okay, so that's what it is. Now, okay, So one thing we need to add to the model, that we need to add the probability of going from a state to another state. So let's say, for example, I am in a state here S. All right. I can go to S prime or S double prime, for instance. So now I can go here with a probability of 0.2 and here the probability of 0.8. So these are probabilities, right? And I can, once I go to this state or I leave this state, I have a reward of, let's say my +1. Okay, so this reward عادة نكتبها جنب state +1. This is the reward +1. Okay, so you can associate the reward probability of moving from a state to another state. Now ممكن الآن حدخل الأكشن which means I can have I can say that moving from one state to another state and taking this action. I'm moving to from one state to another state, and on the way of moving to that state, I'm taking an action. So let's suppose, for example, that the robot is moving from this position to another position and taking the action of emitting, for example, a music. Okay, so that's an action as it moves from one state to another state, because I told it once you cross to, let's say, for example, or once you come close to a student, أعطي إنذار، أعطي warning. Let the student know that you are around them، خاصة في الامتحان. يعني ممكن gentle beep حتى الستودنت ما يرتعب من الروبوت if this robot is proctoring an exam. Okay, so this is an action, but the robot is moving from a state to a state, but it's taking, as it moves, another action as it moves from a state to a state, meaning from one position to another position. It can take images, videos. That's action. Okay, so it can produce sounds, it can take images. Those are actions, but moving from one position of the room to another position, that's from state to a state. فبدنا نفرق بين الأكشن. أحيانا in some problems actions with states they become identical, and these are simple problems. But for problems المعقدين لا. Take the cleaning robot, robot which cleans our house. As it moves from one position to another position, from one location to another, from one state to another state, it might decide to vacuum. It might decide to see a lot of dirt. لا, it applies شوية soap وبتحك يعني rub it, and then action. It's taking the proper action. Okay, so moving from a state to a state is one thing, and taking an action is another thing. Okay, so and that's what we are saying here, that as we move from a state to a state, we can take actions, right? Certain action, and we can have a probability for that, and we can have reward for that. Let me go for an example here. Okay, more of agent can be classified based on policies, okay, or based on models. Okay, these are separate classifications. بس أنا حقيقة اللي بحب أنا أركز عليه لأنه هذولاك إن شاء الله will pick them up along the way, which is model based based on model classification, model free on model based. حكينا عنهم قبل شوي. Model based means what? It means I have given the model to the robot, to the agent, meaning the robot is supposed to proctor this exam. If these chairs are fixed or seats are fixed and this podium is fixed, I can take the plan, give it to the robot, says, robot, this is the floor plan. Okay, the model is given to you. Now proctor the exam. Okay, but if I manufacture a robot that goes to any university, to any academic setup, to any academic institution, and start proctoring like that, this is model what? Model free. I did not give it to the model. Now learning أصعب أو عفوا الactions أصعب للروبوت, because first it has to learn the environment by itself. I don't give it the model. Then it start taking actions. Okay, so when the environment is not given, this we call model free. وعادة الالgorithms أصعب, right? لأنه I did not give it. وهذه real life situations. Like when I am using reinforcement model to implement atomic driving. يعني, the driver, the car drives without a driver. So this self-driving cars, you think they are model based or model free? Model free. You can't have all the streets in the world given as a model تعطيها even if you do, sometimes we have a street في road closure, في accident, في road work, there's a water puddle. Okay, so the environment في ازدحام, I have to change the road. Okay, so it is obviously model free, and this is real time environment. Okay, this is an example of just to show you how we I want to go from start to end. Obviously, and a learning algorithm will go through these steps to go from start to end. But this is the differentiation between policy, okay, and value function. A policy, when in every state I have a directions that says go front. So if I'm here, okay, let me pick a color here, probably blue or green. Okay, so if I'm here, I'm following the policy, right? But طبعا هاي البوليسي ما جاتش من بلاش. After I learned the system, after the robot learned the house, it builds a policy in it, or it builds the value function. واحدة منهم بتكفي. يعني بتيجي هان تقول okay, reward minus 16, which state give me best, this state, then this state, then this state. جيت هان لا هان أحسن بينها هان بعدين هان بعدين هان بعدين هان. Okay, so it follows the state which has the highest rewards. Okay, which is very similar to policy. Okay. Of course, here we can have this for the probability and the actions, and we'll get into that later on. But what I want, so the issue of reinforcement environment relies on exploring the environment. Okay, for complex environment, this can be challenging حقيقة. But I want to reach this slide, which is very important slide in the sense that it shows me that we will use the classification of the reinforcement learning algorithm based on whether I have a model-based or whether I have a model-free. Okay, we're going to cover in the next classes some of those, but really in the model-free, you can see there is a policy-based and a value-based. They compete مع بعض. بس I prefer it value-based, and we'll see that we will teach you the Q learning. We'll go over quickly over SARSA and some of the DQN. But this is the Q learning. حقيقة is a major algorithm in the reinforcement learning algorithms. Okay, and let me with that I conclude my session. And this is at this point I'm going to stop the recording.